Good morning, students. Welcome to the course of Atmospheric Physics, PHU 5302, right? So I hope that you all have gone through the LMS. Actually, I couldn't upload all the things in advance, but due to the things happening in our department during last few weeks, we were also very busy. So hopefully you have gone through those. Have you checked the discussion topics in the LMS? And have you tried to answer one of these? There are two questions. Maybe not, but you can try out those questions anytime during this course, right? One is specifically connected to one of the session of the course, but other one is a common one, which you need knowledge from all the sessions of the book. Basically, the last one is mainly, but you need all the information you are learning, not information, the theory, everything to answer the second discussion topic, right? And I hope that you can answer and give a good suggestion, which I'm asking in that question, right? Please check that. Okay, let's start our session today. Only 1 minute is there, but I will share the PowerPoint with you. Before that, you need to know whether you have gone through the course material also. Unit 1, that's the book that we are starting today, session 1 to 3. I'm trying to cover first 3 sessions today within this limited time period. Usually, when I'm teaching you, I'm giving lots of information, facts, and I'm explaining the theory, right? But in the background, there are so many questions that I'm answering to you, right? You need to capture all the things what I'm teaching, even in the online way or after the session. You can, I'm putting the recording into the LMS, then you can refer the recording also, and then try to understand what are the basics and theories I have taught you. These are the things coming into the NBTs and final examinations, right? So, but you have all the past papers in the LMS since this course starts from 2018. The new one, earlier that there were different types of course material. So I wrote new course materials few years back, right? So you have to go through the past papers and check whether you can answer the questions by yourself effectively. Because within the registration time, I heard that some students told me that this course may be very easy for them to pass, right? It's okay. Yeah, I agree with you. But for the students who have done their homework, not for the other students, right? You can check the past papers and find out whether it is right or wrong, right? So usually you're not aware within the NBT 1 examination about the course material and what are type of questions you'll be asked, right? But after you getting the marks of NBT 1, you will realize, right, what's really going on. So I'm warning you, I'm giving you some hint in this time. You have to work from the beginning, and you have to go through the questions and review. There are so many review questions in the another forum in your LMS, right? Sometimes 25 questions for one session, likewise more than that. Sometimes some sessions have number of questions. These are the questions given to you to check your own knowledge, whether you fit into this course. Otherwise, don't ask me to change whether you have some problems and you have low eligibility mark, and you don't have eligibility and you have low NBT marks, right? I'm not considering those, because now I'm warning you and now I'm instructing you carefully and clearly what to do, right? So no excuses are accepted within the total course period, right? Because this is a actually simple one if you study. And I'm trying to give my best to you and trying to help you in every way, right? So I'm your teacher, and I'm trying to teach you what I know and what I can get the outside world to teach you, right? So let's start. I'm sharing the PowerPoint with you. And from the also, I'll put another announcement in the LMS uh, um, for NBT1 examination information. Still, I haven't decided which sessions I'm considering for NBT1 examination. So I'll put that announcement into the LMS later on, right? Because it depends on the some days course I can hold within the first month before the first NBT1 examination. I'm trying to put extra workshops also other than this days course, because it's not enough for me. And so depending on those situations, I will inform you mm, which sessions are assessing in the NBT1 examination. Hope you're clear about the course now. Okay. In this course, we are going to learn about our atmosphere, but within a different angle. You may have seen the air, the sky, and maybe you have felt the coolness of the wind, whatever. But here in this course, we are going to learn about the physics behind that, right? Before starting our lesson, I would like you to ask something. Please close your eyes, right? But because we have a small exercise for you. And after closing your eyes, take a breath right now and think of it. Okay. So what do you breathe? Okay, you can open your eyes. What did you breathe? You breathed oxygen, right? That means you need oxygen to survive, right? Where do you find that oxygen? From your surrounding, the air, atmosphere, right? It is a thing that makes up that oxygen consist, right? So atmosphere has 21% of oxygen. So that oxygen is the thing that we need to live, right? So you need now know we can't live without atmosphere. So let's learn about that, right? So you know this is the Earth. If I will show you, this is the Earth. This is the Earth limb, right? The horizon, right? There's a blue line here. It's sometimes called atmospheric limb also, right? It is this thin layer is atmosphere in our Earth system, which is protecting us, right? It is a kind of thin veil of gas molecules. And with that thin veil separates the Earth from the cold emptiness of the space. Right? It protecting from all the extreme events happening in space. Right? And high energy particles, whatever. Right? So this has been observed by the International Space Station for years, decades, right? So they have seen our atmosphere as this thin line over the Earth limb, right? Atmospheric limb. Sometimes it can appear as a blue hue, right? Line of blue hue. Sometimes it is orange when it is sunset or sunrise, right? Likewise, we have observed our atmosphere as a thin line around our globe. But this thin line is protecting us, right? And uh, who gives us the energy to survive in this world? Sun, right? So, but in our solar system, there are number of planets, but our planet is the only one who have uh, living beings, and we'll see who is responsible for that and why it's not happening in the other planets. Do you know? Mainly because of our atmosphere. There may be some other reasons, but everything connected to our atmosphere. So you're going to learn about this important layer, important line, blue line, right? And while learning this course, and I'm trying to teach you the importance and the physics and also the theories and how we can derive the theories, right? And how we can see the evidences to the data, not directly data from the theories what we are going to derive, right? And finally, you may understand this is not a simple thing, what we look at, the blue sky, right? It's a very complex system which has so many functions. It regulates temperature, recycling the water within the biosystems, right? Or other systems, right? So many things happening within the atmosphere, and sun is supplying the energy for us, right? But what happened during last decades, last century? We have changed it. The natural rhythm of the Earth system has changed due to us. We have emitted so many uh, gases which are not uh, persistent in the atmosphere for a long time. Time to time, we are emitting carbon dioxide, carbon monoxide, so many things into the atmosphere due to our uh, functions. So it has changed now from 80 last century. You know that the red dash line is green has a lot. Thick line is the observed one, right? And observed carbon temperature anomaly from the average, right? During the past century. It has changed up to high levels, the anomaly, the difference between the average and the observed, right? So this has affected in all the situations in our world. One of the situation I selected here, you have a question in the LMS, so you can choose another other things which are affecting our climate and what we have altered during the past decades and past century. And you can answer that question uh, throughout the criteria what you have selected. You can select anything. I have selected here the ice, sea ice, which is giving some evidence of changing climate, changing weather, changing earth system, changing atmosphere system. I have selected here one thing, but there are so many things. I have given you some resources. YouTube, maybe you have some other resources. You can find out lot. There are AIs you can get here some help. So whatever the resource you are familiar with, you can choose any kind of weather element or whatever to find out what we have done throughout the century, which is altering the earth system and atmospheric system. Because the other point lying behind that is the important thing for us. Otherwise, we won't survive here. Our whole Earth system may be like Venus or Mars. We'll see why it is not and why it is going to be like that, right? That's why I put that question into the LMS to get your support, get your suggestions to changes. Because we can't change by alone. We have to change the whole world or whole country together, and we can have collective decisions. One can't change one thing, a whole thing. We have to have it, and I think this course is very suitable in this time period. Actually, it's timely in today's situation, thinking of the whole world, right? So you may understand the importance of atmosphere and protecting it. You know, in the Europe, USA, right? They're having a big problem because of heat dome. They are suffering a lot. Even Iran, they have cut down the water supply. Then have given vacation for the workers. In China, they can't walk along the roads. Their slippers are melting due to the heated tar, right? So whole world is in a mess. Even Sri Lanka, we are suffering. We don't have usual monsoon rain. Now we are having, but we had a very difficult time few days ago. You know what happened to us? Whole world is suffering, and we are also part of that. So that's why I'm telling you to find out the reasons within your interest, right? I'm not telling you what kind of thing that you have to choose to answer that question in the limits, right? So I have chosen here sea ice, and it is melting. The sea ice this is a Arctic region, Arctic sea ice, not Antarctica. The sea ice extent with this date, September 19th, this is this much. But the line, you see, there's a line, the orange line shows the 1981 to 2010 average. See how it has reduced, right? So sea ice is rapidly declining. It is not restoring back because of the heat in the atmosphere, right? So we have changed our whole world, and even the sun is supplying the energy, even the Earth's atmosphere supplying moisture, and we need greenhouse gases to survive. We will see, and aerosols also need small particles to have rain, right? And ocean is supplying fresh water, gases, chemicals, yes, everything, and land is supporting or to survive us through food, through vegetation, soils, right? So many things. Even our earth system is helping us in everywhere where we are destroying it without having sufficient knowledge. I think even the people have knowledge, they don't know what is going to be in the next few decades. That is also not knowing now. So I hope we can understand, learn, and do something. Let's go. I have a few questions to you before starting this. Okay, when uh, the atmosphere. It is around the globe, as you see in this here. You see this is a blue marble, which are seen from outer space, our Earth. So what holds the Earth atmosphere in place? Why it is not disappearing into space, and what is the force behind which holds the atmosphere around our Earth? Can I have asked anyone? I need to find. Okay, I'll ask someone. 42146. 421462885. Can you unmute and answer? It doesn't matter. We will answer in wrong way. I'm not caring about that. You have to answer anything. What force holds Earth atmosphere? Why it is not disappearing into space? Who holds that? Okay, we can give we can give that chance to any other person who is voluntarily willing to answer. Hey, Shani, Dinet,
Gravitational force, Max.
can you tell it loudly?
Gravitational force, I think.
Yes, gravitational force, right? Yeah, yeah. This you have to listen and answer, right? This is not for one person, for all, right? Okay. Gravity holds the atmosphere to the Earth's surface, right? It's a gravitational pull, right? The second one, is atmosphere a mixture or uniform layer? What do you think?
It's a mixture of multiple gases.
Okay. What are the things behind your answer? Why do you think it's a
It's a
mixture?
homogeneous mixtures of gases.
Homogeneous. Okay, we'll see. Right. Are there any other answers?
Mixture of different gases.
Yeah. Thanks for all the answers. Right. Yeah. The answer is it's a mixture of gases, solids, and liquids, right? Small particles are there, that's why I put solids, right? So it's what are the things behind this answer? Key points. Actually, our atmosphere has a variable composition: nitrogen, oxygen, carbon dioxide, and also soot and water vapor. Everything is there. So and we have a layered structure. You will see in the second session, right? So it is not a uniform one. It is a layered structure which has different characteristics. So it's a mixture, right? And how does the atmosphere extend from Earth's surface to outer surface? Can you guess how thick the atmosphere is? If you have read the book, you can answer it too.
The thickness is reducing.
Hey, yes, yeah. And can you guess how much kilometers? How thick it is?
480 kilometers.
Yeah, 180, but it is also approximate one depending on the theory, right? Yeah. But we see, there can be different boundaries, right? It's a purpose dependent definitions for each boundary. Your 180 is actually the accepted one, right? Because usually the NASA uses this level for their orbital trajectories, right? So that's why they're considering Earth's boundary is 480 kilometers, right? But it depends, right? There's a line called Kármán line within after 100 kilometers from surface. That is a distance the aircraft flights can't fly, right? The kind of arbitrary boundary for aviation, right? That is sometimes within the aviation, it is their line for the atmosphere boundary, right? For the NASA and space people, they are using 480 between 500 to 600 kilometers, right? Because they have choose because the particles in that line or that distance, particles behave independently. Collisions become very rare, and so they have chosen that boundary. And sometimes for big calculations, they are using some bigger boundary, magnetopost boundary, 10,000 kilometers. Its magnetic field overcomes solar wind or space, right? So it depends, but we roughly think it is as 480 kilometers, right? And the fourth question, where does Earth atmosphere end and outer space begin? Tricky question. I'm not asking here the thickness here. How do you find now?
After the thermosphere,
Okay. Any other answers? No definite boundary because it's gradually thins until it merges with the space, right? Actually, this gradual transition is done by the layered structure of the atmosphere, physical processes, and our changing particle or molecular behavior with altitude, right? So we will find out some deeper things behind all these problems within this session and beyond those. Also, not only those sessions, there are so many questions I can ask. I just thought to have a few questions to aware you what we are going to learn, right? So, as I told you, it's kind of a blue marble, which you can see from outer space. That white things are white swirling clouds covering the oceans and land masses, right? See, this blue marble is the only planet in our solar system which can sustain life, right? I need some answers for this also. I told you that only the system which has life is Earth. Why? What is how the atmosphere protect us? If we think atmosphere as Earth's vital protective system, not any other thing, only the atmosphere. What do you think? Let me know your answers. කොහොමද atmosphere අපි රකින්නේ? Time to time I'm explaining very briefly in Sinhala, but basically I'm not using because there are so many Tamil or medium students here, but I can't teach in that language, so I'm basically using English, but time to time will brief in Sinhala. Let's know why is an atmosphere important for us? as a protective system. It's giving a special keyword, protective system. කොහොමද අපි රකින්නේ? I have asked that question in the exam also. Someone is typing, yes, yeah, Varnasurya, here, atmosphere protect us from the sun. Yes, that is one thing. What else? මොනවද කියන්නද? තව මොනවද තියෙන්නේ? Harmful radiation is one of the things now. What can we live without atmosphere? It provides oxygen to respiration, right? Yeah, it blocks harmful solar radiation. Not only that, it blocks meteors also, space debris, right? And can we survive without atmosphere, without freezing, right? No. Because atmosphere is the one who regulates its temperature through greenhouse gases. There's a natural greenhouse effect, right? And it's a system which drives weather and water cycle. I'm not giving the answers, I'm just try to provoke you, right? So, what else? Can we hear sound without the atmosphere? No, it is the medium that's supplying to enabling the voice or music, right? Otherwise, we can't communicate like this. What else? There are so many other important things, but let's summarize this. But you didn't answer. Okay, first one thing, if you think about life, how it supports us, providing oxygen, supplying carbon dioxide for photosynthesis. Otherwise, we don't have food, no? So, and maintaining stable atmospheric pressure. Think about if we don't have stable atmospheric pressure, what will happen to our body? We'll come to that section in the 8th session, but it's better you think before that, right? What will happen to us, to our body, if we don't have a stable atmospheric pressure? And it regulates climate through the greenhouse effect, moderates the global temperatures, and distributes heat via atmospheric cycle. Otherwise, the equator will be very hot and the pole regions will be very, very cold. But atmosphere distributes heat through convective currents. But there are big currents, right? Not as the small bubbles what we think of our Earth's surface. Big loops in the atmosphere which distribute heat, distribute moisture, right? And while it's distributing moisture and while it's supporting its surfaces through water vapor to ice, it maintains the planet's water cycle. Then, as one of the students has put into the chat, it offers protection for us. It shields against harmful radiation, UV, extreme X-ray radiation, our other cosmic energy particles, right? And also it burns up incoming meteors. Otherwise, think about other planets who don't have atmosphere. They have big craters, no? Then we like them. So, and also, without atmosphere, we will scorch, right? As we experience in the Europe these days. It reduces extreme temperature fluctuations, but it's not a problem of atmosphere. It's a problem of us who have changed that atmosphere, right? So, and it enables essential processes. Not only oxygen, it supplies by all the cycles, biogeochemical cycles, and it allows medium for the sound transmission. And it is the one who facilitates weather patterns and precipitation. Otherwise, these cycles will vanish, right? And no life will here and no one is here to talk or to listen, right? So this blue line, right, thin blue line is protecting us. You have seen two lines there. One is white and one is blue hue. And the white layer mainly light scattered from the atmospheric aerosols, and the overlying blue layer is mainly light scattered by air molecules, right? We'll come to that parts in the later sessions, but just think about that. One day you have to have knowledge to teach me even, right? So all these things makes the earth livable. All these processes, functions, right? So do you agree with me? Earth's vital protective system is the atmosphere. One can argue with other things, but we have strong evidences. We won't be here without the atmosphere, right? Then, Earth is not only a vital protective system, it is also a blanket, thermal blanket. How it is happening, right? And there's a figure about a greenhouse. Can somebody explain to me? The atmosphere is acting as a global thermostat, right? It functions as a temperature regulator, maintaining Earth's habitable zone, right? Through three processes. This is only one processor I given as a figure, greenhouse, right? There are two other things. They are to regulate the Earth's thermal behavior. And I just asked you how it protects us using the greenhouse effect. How the atmosphere act in this scenario. Can somebody explain? I'm going to this concept one by one, but before that I need your answer. Can anybody answer to me how greenhouse effect is protect us and how it works as a blanket?
One of the greenhouse gases, like they absorb the temperatures and remit back it to the earth so that it would retain the temperature.
It will retain the temperature. Yes, that word is perfect, right? Retain the temperature. It is not trapping the temperature. Okay? Carefully use the word. Sometimes it is misleading. The words are misleading. Yes. Let's look into that. So actually it's a atmosphere acts as a natural insulator, right? Which can balance the incoming radiation with outgoing heat radiation using the natural greenhouse effect, right? The greenhouse mechanism helps that. Therefore, the Earth's surface is warmed by 33 degrees Celsius, right? Yeah. So it reduces the extreme day-night temperature fluctuations and actually totally prevents. But sometimes due to the enhanced greenhouse effect, it can be changed, right? So we will have hot nights and as we experienced last few weeks, right? It is due to the other causes now. So, but a natural greenhouse mechanism, I have used the trap, but it is the one used basically in most of the scientific literature, but it's trapping, but there are two meanings for that. It's not totally trapping. Some of the radiation will reflected back to space by the upper level carbon dioxide. Only the lower level carbon dioxide or greenhouse gases can trap some of the infrared radiation, and they can the heat can be retained. Can't totally trap, right? So it has a meaning. So the best word is actually retaining, right? So otherwise, our Earth will be so much temperature will be so much different. Earth's would be average temperature will be minus 18 degrees Celsius. We will living in a frozen world then, right? Because of this natural greenhouse mechanism, we are having a comfortable range 15 degrees Celsius. This is global average, right? Not Sri Lanka. Global average. Average of this much up. In Fahrenheit, 59 degrees, right? So, do you understand? Without this greenhouse effect, that would be a very, very cold place, which we can't live for some animals, but for not the humans, right? And if we check with our conditions with the moon, which has no atmosphere, the daytime temperature is extremely high, can be 127 degrees Celsius. And the nighttime temperature will be minus 173 degrees Celsius. The moon, right? For us, daytime average temperature is 20 degrees and nighttime average temperature is 10 degrees Celsius. So we have this comfortable range because of this greenhouse mechanism, right? So, however, atmosphere is protecting us from regulating the thermal radiation. In this slide, you may understand more things about greenhouse effect, how the solar radiation come, and some of the radiation reflected from the surface or from the atmosphere or the clouds, whatever the condition can reflect. But the reflecting long wave radiation can be, or long wave or infrared radiation can be retained due to the some of the atmospheric gases, carbon dioxide, water vapor, likewise, they have ability to capture, right? So therefore, it is a little bit warmer than the usual, right? Because of that capturing of infrared thermal radiation. It actually, here it is giving the correct thing, right? Sorry. I need to raise a point, right? Okay. It's not trapping, it is slowing the escaping, the heat escaping from us, our whole system. So what it does is it delays the heat releasing. So the delay keeps our Earth in this average 15 degrees Celsius instead of minus 18 degrees Celsius, right? So you see what happened within the right side figure, right? Okay, we can understand this role of our atmosphere if we compare our Earth atmosphere system with the other neighboring planets, Venus and Mars. And Venus has thick atmosphere, which is not like us, right? Which has high greenhouse gases, 90% carbon dioxide is there, its atmosphere. And in Mars, compared to Venus, it is very thin atmosphere, right? And also it has 80% of carbon dioxide, but it's very thin, yeah. So, however, we are having perfect conditions and greenhouse gases are very less compared to the other two planets. It is 0.4 percentage from our whole atmospheric mass, the carbon dioxide, and it can at water vapor can be changed 1% to few percentages, right? So having too many greenhouse gases is a problem, right? So we are having the exact condition it is suitable for life, but due to our work, the humans problems during few of not all everyone, most of us are not aware of what actually atmosphere do for us. So they are emitting lots of polluted gases, including carbon dioxide, and it is not only that, so many other gases, sulfur dioxide, and some gases contribute in various levels to change our balanced atmospheric system, which will drag into one of these situations like Venus or like Mars, right? So that's why I put that discussion topic into the LMS to think about it, right? Next, we will move into because it is already 45 minutes has gone. The next session, actually our sessions, I am putting all the sessions together here to discuss origin and composition in session 1 and structure in session 2 and 3. In the session 1, one of the topic is the origin of the atmosphere, right? In the figure shown in this slide, you see early Earth in the rightward side and today composition of the Earth atmosphere, right? What has changed from that time to present? What has changed actually? What do you understand by the figure? Can you tell me? ෆිගර් එක බලලා මට කියන්න මොකද්ද වෙලා තියෙන්නේ කියලා last few billion years.
Oxygen level is decreased and the argon is increased.
Oxygen level පුතා, it is today the 21%. Can you see oxygen in the earlier පුතා? No. නෑ නේද? එක
Of
වැරදි.
course.
Yes, yeah. So it wasn't there. There wasn't much oxygen at the early atmosphere. You see why, and it's good that you have misunderstood it. ඒක හොඳ වැඩක්. මොකද අපිට එතකොට ගැන කතා කරන්න පුළුවන්. What else? අද වෙලා තියෙන්නේ අතට atmosphere එකට. එදා එකම හිටියේ නම් අපි නෑ හැබැයි, right? We are not here if we have the same atmosphere as 44.5 billion years ago. What happened? There's no oxygen and carbon dioxide 18%. Now it is 0.3.03. Probably someone has answered. Okay, someone is typing there. Right, yeah. Yes. Okay. There some students have typed in their answers into the chat box, but I prefer others to open their voices, right? Because we need to discuss together. Yeah, water vapor is 1%. Even now also it's like that. It's not much different. Argon is argon is there. Nitrogen is a bit varied, right? It's not a perfect picture which shows the early atmosphere, but roughly, right? Okay, we know Earth's first atmosphere formed 4.5 billion years ago. Actually, we consider two theories. One theory is volcanic eruptions, another theory, right? There's another theory also. Sorry, it's not. And we consider we are actually thinking that our early atmosphere was probably contained nitrogen, carbon dioxide, water vapor, but no or little oxygen, right? Which is very similar to our neighboring planets. And after a few billion years, after getting cold, probably 2.5 to 2.4 billion years ago, right? Water vapor, it has happened gradually, not at once. We have seen that water vapor condensed and oceans, right? So after oceans have appeared in the Earth system, oxygen formed, and there was a ozone layer, right, which protected them from the harmful rays at the upper atmosphere. So our conditions was sufficient enough to have life, right? Not in land, but in the oceans, right? So maybe very primitive type lives. So green plants could be there at that time. So they have started the photosynthesis. Usually, cyanobacteria, blue-green algae have been used sunlight to convert carbon dioxide and water vapor in the atmosphere to make sugar and oxygen, right? And we call it as a great oxidation event. So it happened long time. It slowly filled the air with oxygen, right? So, sorry, oxygen. So that's the history with what we assumed, the transition from early atmosphere to present day atmosphere. Early atmosphere, it was very toxic, oxygen-free world, right? With no life at the beginning, but there were complex life after that, few billions years ago. But the main changes happened during the period, last period was carbon dioxide has decreased. It was absorbed by the oceans and used by the ocean life, like shells, right? And oxygen has increased up to 21% from photosynthesis and water breakdown. We will come to that point later. And nitrogen was not much different, 80% estimated. It is because it is chemically unreactive, right? And it became gradually the dominant component of the atmosphere, right? Because the water vapor condensed and formed oceans, and carbon dioxide as a greenhouse gas, which helped to balance our thermal structure, right? And also sulfur dioxide was there, but it wasn't shown here. It was also there, but it contributed some acidic conditions needed in geochemical reactions, right? This is one of the theory. How our atmosphere began. One theory suggests our atmosphere produced by erupting volcanoes, which spilled out so many things like carbon dioxide, sulfur, right? Some ammonia, all these things, they are guessing that it is due to the volcanic eruptions. And because it is old and beginning at the 4.6 billion years ago. After 2 billion years ago, it has changed by the early organisms. As I told you, cyanobacteria, which used carbon dioxide and water vapor in the atmosphere to produce oxygen through photosynthesis. This is one of the theory they are having, right? But not only that, there's another way that the oxygen can be released into the atmosphere, dissociation of water due to the sun's light, right? So it can also break down water vapor in the atmosphere into hydrogen and oxygen. There are also some probability to have oxygen, but we see today in 21%, right? That is one kind of theory we are having. There's another theory. We think other than the volcanic outgassing, what we saw earlier, right? There can be comet collisions, repeated comet collisions, right? Because some of the scientists have found some evidences, right? Which has they are guessing that some of the proportion of carbon dioxide and oxygen came into our atmospheric system because of the that comet collisions, right? So these are the things that these are the theories behind the changing situation of atmosphere from early atmosphere to up to date, but no one knows which one happened. But there are evidences, scientific evidences. We can argue a lot within these evidences, right? This is the best thing, this is the second function happened, right, guys? But still, scientists are finding more deep, strong evidences to find out what happened throughout the billions of years. What changed the atmospheric composition from more carbon dioxide to less carbon dioxide, no oxygen to 21% oxygen, right? So you can argue your own way, and if I ask a question, you can answer in what you have gathered, right? This is not, I'm not giving everything to you. I'm outlining what is.
Madam, will you upload the presentation and
Yes.
slide recording?
Yes. Yeah. Are you going to leave the session now?
No, madam, but there is a connection failure from time to time. That's why.
Okay, I'll upload it, right? But it's slides and the my teaching is not this good enough to do the problems, right? So you have to go through the book. Course material unit 1, all the sessions within the first few days course, and after that after other units also. You have to read the books, you have to have your own short notes, you have to have your own explanations for the concepts, for the problems, and for the answers for the review questions. Good that you have asked that thing from me. Then I want to again remind you what you have to do, right? Don't think that the slides and the speech is enough for your examination. It's not because most of the time I'm asking conceptual type questions. That to answer the conceptual type questions, you need to have some background knowledge about the concepts. You can find out there are so many resources, right? but I'll put the things into the LMS. Usually I do within few days, depending on my work within the campus. If I can make it as I'm putting into my Google Drive and put the links into the LMS, right? As I don't have ability to put the whole video or whole video to the LMS on the link. Okay, we saw present day composition of the atmosphere. Did you observe something? The composition were made with some components. Some were constant components, some were variable components, variable like water vapor. Actually water vapor is a highly variable component, right? Well, carbon dioxide also considers a variable component. And also, that's one way that we can see our atmospheric composition. But there's another way, main gases or trace gases. We'll see how. These are the basic gases we see in our atmosphere. As you know, it's 78 nitrogen, likewise, argon 0.9. The early slide, I have done a mistake. It was 9%. I think I missed the dot, right? So water vapor, it is fluctuating between 0 to 5, mostly 4% likewise, right? Parts per million, right? Or the ppm means parts per million, right? 308 parts per million carbon dioxide in a sample of the gas taken from the atmosphere, right? Likewise, the ozone is less than 0.1 part per million, but it is doing a big job protecting us from harmful radiation, right? And I have divided all the components into the constant components in the yellow and the green panel, variable components. Water vapor, carbon dioxide, methane, all are variable components or trace gases. These are the main gases, right? In main and trace gases here, shown here. And water vapor changing 0 to 4, right? Okay, I need to ask another question from you. Nitrogen is 78%, right? And it is unreactive. So that's why it is a dominant gas in the atmosphere, right? And water vapor can it be a variable gas or highly variable gas? And what is your argument? What do you think? Water vapor can change into what, 0 to 4? No? What do you think? Is it a variable or highly variable? Okay, before that we will find out what is the definition for this constant, highly variable, and variable. Actually, constant components means which has nearly fixed proportions. Nitrogen 78, oxygen 21, argon 0.93, right? Those are constant components. So nitrogen acts as a neutral buffer. It prevents rapid oxidation, right? It actually dilute the oxidation event. Otherwise, we will have a lot of fire, right? So oxygen 21% in the constant components is essential for our life and us, right? And argon, it's a kind of inert gas, and it is there from the beginning of our Earth system, right? And variable gases. these are the gases which fluctuate but maintain global average. Small but critical, right? So there the carbon dioxide 0.4 is, right? And also ozone is a variable gas. Even it is less than 0, it is a variable gas, small but critical. Methane, it's kind of a short-lived gas, but it is increasing today because of our work, right? Due to the fossil fuel and agriculture things that it is coming, increasing rapidly. These are the variable components. Highly variable components are, it's fluctuating very rapidly. And we can't have a global average like water vapor. So one of the greenhouse gas also, in water vapor is a greenhouse gas, right? And aerosols, they're highly variable because we are emitting, it's a localized situation, depend on localized situations, depending on the pollution, depending on the volcanoes, depending on the things what we do to our atmosphere, aerosols can be changed. So it's a highly variable component, right? But the funny thing is, even the carbon dioxide, water vapor, aerosols are variable components or highly variable components. Sometimes methane is less than 1%, right? They are the ones dominating our weather system or climate, right? Other than the nitrogen, which has 78%. Think about that, right? So it is, these are the lines actually we had to think, key things. But because of our diluted idea about the nature of or importance of our atmosphere to which sustaining the life due to our activities, our human activities has disrupted this delicate balance, right? So even it is less than 1 point, we have to have balance now. So our activities has disrupted that delicate balance, that natural balance. That's why we have experienced the accelerating global warming today. So understanding the things behind what the each component is doing, why should it in this amount, will help us to think about our future or predict our future, right? Otherwise, we'll be in a mess or in a hell, right? In some few decades after. If we release the same amount of carbon dioxide, aerosols, or other pollutant gases into our atmosphere in this way, someone has to change the world. Maybe you, right? One of you can do that, right? Someone has to start now. It can start from the Asian country, like us, small country. Maybe not the same way as others do. We can think as the same way and go the same procedures to protect the world. Maybe something else we can suggest, a different thing which can protect us. It is our work. You have to think about that, right? Again, all the things I've divided into constant, variable, and highly variable, and in different colors. Let's go through later. And okay, our atmosphere, I asked you earlier, I asked a question from you, whether our atmosphere is a mixture or layered. Do you remember? So actually, I told you that it is not a layered mixture, it's a mixture, not a one layer, right? So we can have different kind of layers in different concepts, right? We can think about our atmosphere according to the composition, as you see in this panel, or according to its temperature, or according to the electric properties, or whatever, right? Based on the function. So So upper atmosphere can divide into few layers according to the temperature. As you see in this panel, troposphere to exosphere. Okay, as you can see, these answers, right? And again, it can share this is a thermal classification which divides atmosphere into layers based on the temperature changes. So this is the troposphere, right? And stratosphere likewise. These temperature variations influence our weather patterns and also the atmospheric circulation loops and also our functions like satellite operations too. And we can think about our atmosphere dividing it as in the compositional standpoint, as you see here, right? The atmosphere consists of well mixed gases in the lower layers, and we called it as a homosphere, right? And stratified elements in the upper layers. Then my question is wrong here, and answer is also wrong here if we think about the whole atmosphere, but we consider the atmosphere mainly in the lower layers, where we live and think, but directly influence us, right? But if you think about the whole atmosphere, heterosphere is actually kind of a layer which has a stratified nature. Actually, the homosphere maintains stable mixture of nitrogen, oxygen, and other trace gases like argon and carbon dioxide, right? But in contrast with that homosphere, heterosphere has separation of gases according to molecular weight, where lighter elements like hydrogen and helium at higher altitudes, right? While others in the lower, it has stratified, right? And then again, we can look at our atmosphere according to the electric properties. Electrically, the atmosphere contains two critical layers, ionosphere and neutral atmosphere, right? But it's not there. Ozone layer is there, but it's not directly due to atmosphere. We have ozone layer, ionosphere and neutral atmosphere. Ozone layer and layer without ozone is the actual limitations, right? This electrical structure, right, in our atmosphere, due to this ionosphere, affects all the communication system, right, what we experience, and space navigations, spacecraft navigations, right? And also it is a kind of a layer which protects us from harmful solar wind, extreme radiation. It stops, right? So together all these systems, we can classify our Earth atmosphere system according to the composition, according to the temperature, and or electrical, as in electrical properties, right? All the things again as a figure, you see red line shows the temperature variation, purple shows the electrical variation. You know, as I told you, it is only the ionosphere. There's no other parties here. The neutral atmosphere. But yellow one is according to the composition, the division according to the composition, right? Thinking about the heterosphere and the homosphere, how the heterosphere has stratified. Actually, stratification is happening according to the molecular weight. The very lighter gases in the upper level and heavy gases in molecules in the lower layer of the lithosphere is stratified according to this way. This is a totally mixed layer, very turbulent due to the convection happening within the layer because of this Earth's surface is absorbing solar radiation, and it is getting heated, and nearby air also getting heated due to the heated atmospheric Earth surface, and by convection and other radiation processes, the whole atmosphere is turbulent, having convection loops, and it has mixed layer. No. From surface to upper level up to the surface, air density or air molecules are not as same in everywhere. Air molecules are densely packed close to the surface, right? Right. So sure. Actually, as you told me, that gravity pulls the gases towards the surface, and so that's why we can see dense layer close to the surface, while spreaded molecules in the upper layers, right? So dense air layers exert more force than the less dense air in the upper layers. So we will feel more pressure close to the ground than the upper layers, right? So because of this nature, we have high pressure close to the ground while low pressure in the upper layers, right? That is pressure. And if we think in the density angle, it is the same thing happening. As you see in the light blue line, right? It is as okay, there's two definitions for pressure and air, but same concept is behind on that, right? Number of air molecules within a air pass, definite air parcel in the lower level or upper level is different between the lower surface and the upper layers. So it is behind the pressure variation and the density variation. Right? So if I ask you a question about why this observe greater pressure or greater density close to the Earth's surface while it is different in the upper layers, you should have ability to explain it using the gravity and also all the things which supports the answer, right? Would be a very clear answer combining all the things, right? Actually, air pressure depends on atmospheric thickness. Pressure is determined by the amount of gas in the atmosphere within a considered volume, right? So, okay, if it is change in the amount of gases in the considered volume is changing, it is changing. So you have to look in that wise, right? So that is pressure, right? Their air density, mass of air per unit volume. It's also same thing behind. Follows a similar trend as pressure. Actually, both have exponential decay with the height. You see, actually, this because of this exponential decrease, as you see in this figure, while we go up in the altitude, it is very difficult for us to breathe, right? If I ask such a question from you, why it is difficult to breathe in the higher altitudes? you should have knowledge to argue, right? And have to build a clear answer. Other than these molecular things, temperature variations also influencing the properties, right? Like what we see here, but mainly the air mass within a considered volume is the basic thing, right? Okay. We can, sorry. So this is a calculation how we find out the mean average pressure over the Earth's surface, right? This is the surface area and the mass. Total mass of atmosphere times gravitational acceleration divided by the total surface area. Mean average pressure over the Earth's surface is this much into the power 5 pascals or 1000 millibars while giving the values that we already have, right? Okay, something else. Before I'm teaching you, I need your things, your inputs, right? We know that we can observe vertical changes in air properties. We discussed pressure and density, right? And not only those factors affecting that we talked about gravity and all those affecting the vertical changes in air properties. I told some other properties can be there. What do you think? Right? Things that affect air pressure. What are the other factors you are thinking? Other than the gravity. But can you suggest something to me? Okay. As you are silent, I will tell one thing, right? Altitude, elevation, right? If you go with the altitude, within the higher altitudes, you will experience low air pressure. Within the low altitude, lower altitudes, you will experience high air pressure. The basic reason is gravity. It is pulling the air molecules, right? Yeah, that is one thing, but which we discussed. And what else? Temperature. Temperature higher also can change the pressure. Higher temperatures may lead to low air pressure, right? And lower temperature may lead to higher air pressure, right? So warm air expands, spreading molecules further apart, reducing density and pressure. While cold air contracts, packing molecules together, like closer together, increasing density and pressure, right? So it is also affecting. What else? What do you think? දැන් මම දෙකක් කියපුවා. තව මොනවද තියෙන්න පුළුවන්? හින්ද කියන්න. අපි තව ගොඩක් කතා කරන්න තියෙනවා. නිකන් හිතලා බලන්න. දැන් පොත කියවලම නැහැ. Okay, it's humidity, the amount of moisture in the air. So more humid air means lower air pressure because water vapor is lighter than nitrogen and oxygen. So moist air weighs less than dry air, right? And dry air leads to higher air pressure. Dry air contains more heavy nitrogen and oxygen molecules, increasing pressure, right? So these are the things that make මට අහන්න පුළුවන් හොඳට ඔයගොල්ලන්ට ප්‍රශ්න. හරි. What are the factors that affecting the air pressure in different angle? ඉතින් හොඳට හිතලා බලන්න, right? The vertical air pressure profile, like as we see earlier, and these are the units we use, and we come to that part, the session 8. So I'm skipping, but only this equation is useful because it shows it is quantifying the exponential reduction of pressure while we go up into the altitude from surface. This is the exponential behavior mathematically, what we see in pressure and density. And we just to the second session now. Mr. Moore. Here we are discussing about the vertical layers of the cell. Just showed you how we can classify the atmosphere from the thermal layers, right? This is a kind of photo seen by an astronaut who was in the International Space Station ISS. Was taken decades back, right? But it is still a very fascinating one. It shows us the layer type classification, right? And you see the orange layer, and then there was a creamish type layer beyond that, and bluish hue is there at the upper part, right? What do you think? Which layer is which? And that it shows troposphere in orange at the bottom, right? This is the black is a dark limb of Earth's at the edge of the horizon, right? And above that orange one, pink layer is lying behind it. Pink to white layer. It's a stratosphere. Higher within the upper layers, light blue layer, which gradually fades to darkness of the space, right? It's a kind of exactly kind which is mesosphere. Maybe it is the light blue one, but the other layers are not much visible, right? So this figure shows evidence it is really layered according to thermal variations. Other than these figures, we can find the evidence through the measurements or observed data, right? Which we taken from kind of instruments using meteorological stations. I know that there are so many meteorologists or meteorological observers in our course who are working in the meteorological department. They may be very familiar with these instruments, right? If they are willing to explain something, they can do that now. I'm giving some space to you if you are there. Okay, if they are not here, so some of the evidences are gathered from radars or Raven sondes, which has ability to capture the wind data also. Radio sonde or Raven sonde are most common instruments which gather upper air data, and from the upper air data they are having graphical evidences which shows layering structure within the atmosphere. Right, I'm going everything. We have few layers from Earth's surface, troposphere, which occurs, stratosphere, which ozone contains, and which is the coolest one, and beyond that, the thermosphere where auroras origin, and the last layer which merge with the space, right? There are some transition zones also, as you see here. Tropopause between these two layers, and stratopause between these two layers, and mesopause between the last two layers. Not last before last, right? Then, if we go through these explanations about the first layer, the troposphere, It's actually the Earth's dynamic weather. It includes all the key concepts what we experience in the atmosphere, right? Actually, it can change from latitude wise. Can be 16 kilometer at the equator, while it is 8 kilometer range in the poles, right? What is the reason why there is two different levels between the equator and the poles? Can somebody explain? කාටරි කියන්න පුළුවන්ද? ඒ මේ වගේ two boundaries දෙකක් තියෙන්නේ troposphere එකේ within the latitude wise equator and poles වල කාටරි කියන්න පුළුවන්? Please open your voice. මොනවා හිතනවනේ කියන්න ඒක. මේක આવුත් exam එකේ මම උත්තර දෙන්නෙම නැති එකපාරට මෙහෙම ඇහුවොත් උත්තරයක් එන්නේ නැද්ද ඔයගලන්ට ඔළුවට? equator එක මොන වගේද? What kind of situation at the equator? It is very hot. There could be thermal expansion. That's why we see the troposphere is such much with 16 kilometers. At poles, there's such no heat retention is there because පොළව ඇදයිනේ අංශක 23මාරක්. එතකොට we don't have such a hot climate at the poles. So thermal contraction. It is a reason for 8 kilometer width at poles, right? Now, හොඳට ඔයගොල්ලෝ ගලප ගන්න, right? You have to have the ability to answer that clearly. I just mentioned the cross. Okay, what else? It is a surface layer height. And it contains some other things also. It contains 99% of water vapor within its mass. And 75% of atmosphere mass is in the troposphere. See how thick it is compared with all the components of the atmosphere, right? Within the 16 or 18 kilometers, right? Then what happened? It is there are some marked characteristics in the troposphere. There's all the clouds because the Earth's surface getting heated due to the sun's rays. Then the overlying layer is getting heated too, and atmospheric turbulence can be generated, right? So there can be local changes due to the other wind characteristics, but there can be local changes, and average temperature can be changed, right? So because of all these things, we can see average temperature decrease within 1 kilometer as 6.5 degrees Celsius. That's we call as Webb rate, right? And also due to all these things, due to day and night, we can see different variations, most pronounced close to the Earth's surface in this layer, right? What else? We talked about the composition-wise, 99% atmospheric water and 75% atmospheric mass, right? What else? What are the other features you can guess about the atmosphere? This layer. I told you that it is the totally solar-driven circulation due to the heating Earth's surface, right? Equator is getting heated due to direct sunlight and compared to the polar regions. Due to the resultant difference between the thermal behavior of polar and equatorial areas, we see global circulation modules, cells or loops, right? So it is another thing that we can see here. And also due to the surface heating, we can see convective processes. Therefore, we are having clouds can be formed and can be dissipated, right? If the region having all their sinking area, we can see cloud dissipation also within the troposphere. And stop for a moment, some traction. Heating Earth surface is not only the cause for turbulence what we see in the troposphere. There can be surface friction which make mechanical turbulence, and wind shear can also affect it, right? Which can be the other sources of turbulence, right? And pressure is different because of the temperature variation at the layer. Moisture content is time to time changing, fluctuating very much, and also seasonal migration of the solar heating is also affecting the surface pressure in this layer, right? And all those things happening in this lower layer, right? So there are some other points explained in the book. You had to have your own note for this, right? If I ask you to write a short explanation about the main features or key things that you observe in the troposphere. The next one is the boundary between the troposphere and the stratosphere. It actually acts as a lid that limits the vertical mixing of air, right? Otherwise, you will have a towering thunderstorms. If you don't have a troposphere, it is a lid which limits. No, so it limits. Nothing can be go beyond me, like, right? So it limits the vertical mixing of air. So troposphere is actually playing a big role in weather and climate. Even it is a small layer, which is not very prominent in this troposphere, tropopause, right? Actually, in the troposphere, temperature decreases with altitude, no? But within this tropopause, temperature stops decreasing and becomes constant at everywhere within that tropopause. But we can say slight variation increase but somehow it is act as a temperature inversion. This layer. So this temperature inversion actually act as a lid, and it prevents further upward movement of anything like air currents, whatever, right? Which is trying to penetrate the tropopause. And the width of the tropopause can be 16 to 18 kilometers, not with the height, right? Sorry, with at the equator, but can be depending on the altitude. It can be like 8 to 10 kilometers in the poles. Mid latitudes can be 10 to 12 kilometers, right? So you know, there some jet streams are within this tropopause. Polar and subtropical jet streams actually not within the tropopause, near the tropopause, not within, right? Which is near the tropopause, and it is influencing global weather. And also it is a lid for ozone transition. Below the tropopause, ozone is gas, but above it is very high ozone level, right? So it's kind of a lid. And you know, it is also mm, some other things are happening, not mentioned in your book, right? You know, there are two processes can be happen. It can transfer stratospheric ozone into the mid latitude and water vapor into the back into the stratosphere, again to the stratosphere. So the tropopause is the lid or protection layer which blocks pollutants and excess water vapor entering into the stratospheric layer. But some in times there can be parts to do that. It is naturally happening. It is not a problem. The stratospheric ozone intrusion into the troposphere is a natural phenomena, right? But not discussed much in your book. It has actually happening where the tropopause falls, where the tropopause bends downward. That's such a case, allowing ozone-rich stratospheric air to enter to the troposphere, right? Sometimes jet streams and low pressure system enhance this situation. Even though sometimes deep convection within the thunderstorm situation, and sometimes mountain waves, wave breaking situations can reinforce this phenomena, causing stratospheric air to move downwards, right? That is one kind of situation happening in the tropopause. And also another thing, as I mentioned here, water vapor can be transported to stratosphere through this tropopause bending. Not bend, it is kind of a overshooting, like, right? Not bending upwards, overshooting. So strong convection allows such a situation. So that at such a situation, water vapor can penetrate the cold tropopause and inject into the stratosphere, right? There are some concepts also. I'm not going to talk about those things. So somehow these things are happening. It can, you see, this is a figure about taken by NASA. You see that, as you see, this is the top of tropospheric clouds, and about that the tropopause, you see, very stable, and nacreous clouds, which is formed in the stratosphere, is, you can see that also all the three layers are visible. And next layer is stratosphere. It is also a very important layer, right? Because why? I haven't explained it here. ඔගලගේ වචනින් කියන්න බලන්න ඇයි ඒක ස්ට්‍රැටොස්ෆියර් අපිට ගොඩක් ඉම්පෝටන්ට්. අපි නැහැ ඒක නැත්තම්. මොකද හේතුව? මෙතන කියලා නැහැ. මෙයාගේ ලේයර් එකේ ඒ ස්ලයිඩ් එකේ කියන්න බලන්න. It's the second layer of the Earth atmosphere. It's anywhere extending from Earth's surface. When you go up, right? What is the importance of stratosphere? මොකද හේතුව? ඇයි මේක නැතුව අපිට ඉන්න බැරි? මේ stratosphere special reason දෙයක් තියෙනවා. It is said there. This occurs because ozone is actually packed here in this stratosphere. So within some extent, right? As you see here, ozone layer. Actually, it's in between 15 to 35 kilometers, right? This ozone layer, which contains ozone, can block actually 97 to 99% of harmful UV radiation. Do you think how important it is, right? So it is otherwise we will burn with the UV radiation or high extreme solar energetic radiation, right? So that's why this layer is very important for us. But unlike the troposphere, temperature increase within this layer. Why? Ozone within this layer absorb UV radiation and make it heated. But as a average, it is a stable layer with dry air. Because there's no much water vapor, so and also no vertical mixing. So with minimal vertical mixing and with very little water vapor, so it is a stable and dry air within the stratosphere. And some commercial jet aircrafts fly in the lower stratosphere, right? Because they need to save their fuel to avoid the turbulence which is common in the lower layers due to the turbulence nature existing and those layers and those tropospheric conditions. So and some weather balloons can reach also. As I told you, the ozone layer, as you see here, 15 to 35 kilometers, right? It's protecting us from the UV radiation, and you need to have ability to explain it via question, right? Some kind of spectacular things also there. The stratospheric clouds or PCS, or nucleus clouds. Actually, what are they? If I told you there are no water vapor much, but such type of clouds, it's rare. It's clouds that fall in stratosphere within 15 to 25 kilometers, right? But not in the equator region or polar regions where extremely cold weather exists, right? We can see such type of PCS clouds. Actually, you know, even water vapor is rare in such situation, right? Such type of clouds can be formed due to some other reasons other than the water. There are two types of PCS clouds. Type 1 PCS or type 2 PCS clouds. Type 2 PCS clouds are depending on water, made of super cool water droplets, right? Made out of it. So it is a very rare clouds form at very cold temperatures below minus 85 degrees Celsius, right? But there are other type 1 type PSC clouds, not PCS, right? PSC. I'm so sorry. I have done a mistake when I'm talking. It's PSC, right? Polar stratospheric clouds. That type of clouds can be made of nitric acid, HNO3, and water ice. Less colorful, appears thin grayish layers, right? So that is a very harmful type of cloud. You know, we like clouds, but PSC type 1 are not welcoming thing to our Earth system. It is a kind of a critical thing which helps in ozone destruction because it provides surfaces for chlorine activation, right? Which in other words, it is destructing the ozone layer, right? So these are, in other words, it is helping PSC1, but PSC2s are not such like that, right? So these are the clouds we see. And stratosphere is not filled only with the nitrogen, oxygen. it is now filled with other things due to our functions from fluorocarbons and methane, nitrous oxide. All this the things we are emitting is filling the stratosphere. Then things are getting worse, and ozone destruction is happening in rapid way, right? And all these things linked to the ozone hole, right? In Antarctica's PSCs also, this other type of clouds also influencing, and the things what we have doing to our atmosphere is also influencing. So all these enable destruction of the ozone layer, right? So if I ask a question, how these type of gases or man-made chemicals such as CH4, nitrous oxide or CFCs facilitating the ozone destruction, you need to have some knowledge and gather from other sources and have ready to answer a clear question, clear way, right? Or question in a clear way, right? Not a clear question. Your answer should be clear to the question if I ask how it is happening. And there's another boundary, stratopause between the stratosphere and the mesosphere, between 50 to 55 kilometers, right? And it is very cold, minus 15 degrees, but beyond that, there's a much cold layer, what we call as mesosphere. You see, there's a figure you see, the space shuttle Endeavour is coming back to Earth, and it is directly in the mesosphere, which appears as light blue, and it enters to the stratosphere, right? So this layer, it's a very cool layer in between 50 to 80 kilometers, which is having temperature around average around minus 90 degrees Celsius, or in Fahrenheit 130 Fahrenheit likewise, right? It is the coldest layer. You may argue that is not the coldest, but prepare for that, for your argument, right? Then, unlike the stratosphere, which is beyond this layer, this mesosphere has no significant heat source other than the solar energy. So that's why, as it is high up in the atmosphere, in the altitude, so it goes with height, and the molecules are very rare, very thin layer, less than 1% of sea level pressure existing at that layer. So that's why it is very thin, and very, because of that, the layer is very cold, right? So another thing is, the special thing that we observe in this layer is contains traces of meteorite dust, which actually happening when there are meteorological conditions burning within the layer. So traces of such dust, and there can be nitric oxide also in this layer. So it is also influencing the nighttime clouds in this layer also, right? We can see special type of clouds here also in this layer, noctilucent clouds. Sometimes we call up NLCs, right? And also, other key thing in this layer is we can see some unique phenomena, sprites and elves, very rare electrical discharges, right? They are not thunderstorms, some electrical discharges within this layer, right? So some unique features are there. One thing is shooting stars, where meteors burn up, right? Then the sprites and elves, the rare electrical discharges, and noctilucent clouds, the electric blue clouds near the mesopause. It's higher up in the mesosphere because of ice-coated meteoric dust, which we can visible within the twilight times. So this is the mesosphere. I told you there are some spectacular electrical discharges, sprites, blue jets, elves, like that, right? You have a good explanation here and also in the book, right? Please refer those things. Because I haven't asked much in the exam about these things, but now the time to ask those questions, because earlier times students didn't have much resources to find the things. Nowadays there are so many resources, and you need to get ready. If I ask question, what is the background behind red sprites, right? Or what is the background behind blue jets or else, right? I can summarize a little bit here. So if we think about red sprites, right, as you see here, right? You can see it's massive, right? Giant high altitude flashes, right? Kind of red-orange electrical bursts can be happen at within the range of 15 kilometer, right? And we see like that's sprites as shooting downwards from mesosphere towards storm clouds, right? The thing behind these sprites is positive lightning, rare positive ground lightning strikes. In storms, actually positive lightning storms below, right? Is the reason behind this. The electrical field ionizes the nitrogen, emitting red light. It's a kind of jellyfish, like, right? You see, it's a jellyfish like appearance, right? Sometimes you see it's a carrot type like appearance, but main thing is it's appear only milliseconds. And it is invisible from the ground, but it has recorded in the night vision cameras, and also those are recorded in the earlier meteorological books also. They have observed somehow, but there wasn't some scientific evidences to prove it. So people thought those are myths. But with the development of the technology, nowadays we know it is happening, and it is people have captured it, right? So these things. And then second, the blue jets. These are a kind of upward shooting cones, as you see, blue jets, right? Very narrow blue cones that blast upward, right? From thunderstorm stop to upward sides into the mesosphere. The cause is imbalance between the storm clouds and the ionosphere. The ionized nitrogen emits this blue light, so it's very hard to capture. Actually, it was filmed at last decade, and because as it travels very fast, like 100 kilometers per second, 10 times faster than sprites, right? So it's very difficult to capture. third one, the elves, right? Those are very elves. You see green elves, the gigantic glowing rings, right? Also, they're also massive, kind of expanding red rings can expand up to 400 kilometers. The lower ionosphere near the mesopause, right? So the force behind this gigantic glowing rings is electromagnetic pulses from intense lightning heated electrons. Intense lightning, right? Which heating the electrons, exciting hydrogen molecules, right? That's why we have such a red rings, sometimes red rings. So here, green. Usually it's also very fast, lasts for 1 millisecond. So please try to gather more knowledge and ready for a question if I asked. I told that there are some mesospheric cloud, noctilucent clouds. It's feathery type clouds, right? Made of water ice crystals and can be seen only in rare occasions in the summer, right? And we can't see those things at very high latitude countries. Those clouds are appearing, right? Mesopause is the other boundary, right? Between the mesosphere and the thermosphere, and this thin thermosphere, the layer, outermost layer of the atmosphere. Because the other layer is merging with the space, this is a definite layer what we have. It's actually Earth's hot layer, hottest layer. Some can argue this is even hot, but feel like very cold. Yes, it is true. Feel cold other than cold than the mesospheric layer. But somehow, students, there are some good arguments here. Because I can ask so many questions from this layer also, right? One thing I can ask some astronauts, they feel very cold here, right? Even we call it as a hot layer, because that's why as if astronauts are walking in this layer, they are walking now. They have to wear heated gloves and socks to face the extremities cold condition in this layer, right? So I can ask from such a situation, I can ask a question, right? So this layer, it extends from 19 kilometers to up to 200 kilometers up, right? Why it is having extraordinary high temperature? The thermosphere is containing some atoms, right? Not very dense, but there are atoms, right? Those are capturing the energy from UV and X-ray radiation of the solar radiation, right? That can be maximized when there is solar activity, but usually it is happening. So that's why it can the temperature can be changed up to high levels, right? While molecules here is 1,500 to 2,500 degrees Celsius temperature can be there, right? In the molecule, within the molecules which is heated. But somehow the air layer is very thin now. Therefore, how thin is like that is 10 billion times thinner than the sea level. So, and also because there are no molecules to collide with each other, which is far apart, the collisions are also less. That's why we feel very negligible heat. Even the molecules go up to more than 1000 degrees Celsius, right? So negligible heat transfer makes us, it is a cold layer, right? And one other thing is it is having less molecules, also minimal atmospheric drag is there. So in this layer facilitate satellites to orbit. So therefore, ISS, in International Space Station, orbits here in this thermosphere at 400 kilometer layer because it has minimal drag, orbital drag, which occasionally requires some boost to maintain its orbital velocity. Other thing is this layer, there is no other things to obstruct the sunlight. So no weather or clouds block here. No atmospheric scattering happening here. Solar power is optimized in this layer, right? And there's another layer, what we call it ionosphere. I'm taking some time, more than 10:30. If you need to go, you can leave, but I'll put the things in the LMS, right? But I need to finish this session. But only few things are there. But I'll continue. If somebody wants to leave, it's you have excuse to do that, right? There's another layer. Do you remember ionosphere? It's also overlapping with this layer. That ionosphere is containing charged particles, right? But it is also within this layer. So these are the key things about thermosphere. Please remember that temperature increase and the temperature what we feel is different between thermosphere, and what is the reason behind, and what can happen to different situations. I can suggest a situation, ask you to give a reason for that. But the things, all the things are behind what I have described up to now. There can be some other reasons, but not much prominent, right? These are the things, and there's another fascinating thing binding in with this layer, thermosphere. We call it is aurora borealis or aurora australis. Borealis is the Arctic region one. Other one is the southern hemispheric one, right? It is happening in this layer. Very spectacular thing. As I told you, there can be two sublayers here in the thermosphere, ionosphere and exosphere, because it is also, we can't have a definite boundary, but within this layer, they also exist. And we will go to the last layer, exosphere. It is a layer which merges with the outer space. Where Earth atmosphere meets outer space is the exosphere. So, the outermost one, extending from 500 to 1000 kilometer to 10,000 kilometers, right? And it gradually merges with the space, and it is actually extremely thin and having its own behavior, acting as a gateway between Earth and space, right? Actually it has near vacuum conditions. Air density is very low if we think in astronomical way, fewer than the 1,000 particles per cubic centimeters, which you can compare with the sea level, where into the time 19 times per in cubic centimeters at sea level, right? As particles are so sparse, they are very rarely collide with each other, behaving like individual movements in the molecules or components in the atmosphere. They have individual projectiles, right? So basically this exosphere dominated by light gases like hydrogen, helium, right? Some traces of oxygen, nitrogen, and carbon dioxide can be there, but usually those are the things. As particles are rare, no definite temperature can be predicted, right? So exosphere is such a wise, and if we draw all the layers in the horizontal way, do you see the lower temperature is minus 80 within the mesosphere, edge of the mesosphere, and highest layer is the thermosphere, right? Even though it is felt as very cool. And next layer is ionosphere, Earth's electrified atmospheric layer. At higher altitudes, ions have large mean path. That means have much longer lifetime than lower altitudes. Therefore, in this situation, there can be more free electrons at the levels above 60 kilometers, and that particular region we call as ionosphere and lies between 60 to 400 kilometers. And it is affecting us in different ways, basically radio communication, satellite navigation, and also the aurora events, right? It actually varies depending on the day or night, right? And depending on the season, depending on the altitude, and not altitude, latitude, right? Depending on the solar activity also. It is the ionization happening because of the nitrogen, oxygen, and oxygen atoms. Primary mechanism is photoionization by extreme ultraviolet radiation and high energetic X-ray radiation, right? Which is coming from the sun, right? Solar wind, and it is actually throughout the solar wind, we are receiving such high energetic radiation. When this extreme radiation from the sun strips electrons from the atom, oxygen atom, or molecules like oxygen and nitrogen, then there can be plasmas forms. Plasmas can be formed, that is free electrons plus positive ions, right? So that's how ionosphere is originating. And we have three types of layers there even during the as I told you, the variation of electron density in the ionosphere can change due to the solar activity. Due to the solar flares, more X-rays can be emitted, and it can enhance the free electrons and positive ions. That means thicken the plasma and can have high electron density in the atmosphere, right? I told you that it can have some three distinct layers: D layer, E layer, and F region, right? D is the weak layer with weakest ionization, and it disappears at night. Do you see? It has disappeared. And E layer, right? It's actually 90 to 120 such a distance it is there. It is very helpful for us because it reflects medium frequency radio waves. AM radiation, right? Yeah. And F layer, the farmost layer, beyond 120 kilometers, within 400 kilometers, it can divide into two F1 layers, F1 and F2. F1 is the daytime, F2 persists in the night also. But it is critical for long distance radio communication, right? So this is please observe this. I'm taking some pause and you can observe what is happening during day and night within the ionosphere. Daytime, in nighttime. I told you D layer disappears at night. F1 layer only exists in the daytime. F2 persists in the nighttime, right? This thing happening. What is the reason behind this? Why we see such day and night variation? Daytime strong solar radiation actually maximize the ionization, thickening the layer. Nighttime, there is a process called recombination where electrons rejoin with ions against the ionosphere. Therefore, the F2 layer remains active. I told you that this is right. This is the thing that I have described to now, right? Here you can clearly see the F2 layer only persists, F1 has disappeared, and D is not here in the night time. Only E region is there, right? This is what happened during the daytime. In the night time, as I told you, recombination occurs and some layers disappears. So small exercise is there for you, just a kids thing, right? But it may awake your knowledge what's remaining after reading the book, after listening to the recording, after practicing the things in the book and using these slides, right? Just a simple thing. And then we will move to the other one because the time has gone. But I need to complete this one, magnetosphere, right? There are so many things I can talk about the ionosphere, but we will come back to it in another session. So I'm skipping all the big details. I'm moving to the magnetosphere, Earth's magnetic shield, right? It's the Earth's invisible shield. You know, we are not here without the shield. It shields us from the very energetic solar wind radiation. So that's why we are survive here, but Venus and Mars, they don't have such a strong magnetic field like Earth. So that's why they don't have life, right? But we are trying to go there, right? We want to have camps there. We have to have habitat, make our habitants there also. But think about that. I don't know whether it is possible in smooth way. Can be, but maybe we have to do a lot of things and be cautious, right? So this is the magnetosphere is a region of space surrounding Earth, where our Earth's magnetic field dominates over the solar wind, right? What is solar wind? It's a stream of charged particles emanating from the sun, right? So this invisible shield, the magnetosphere, protects our life and our technology, spacecrafts also, from cosmic radiation and harmful solar radiation, right? it has some shapes, right? You see the front line. Okay, before that, I need to talk about this thing. Actually, what is the source of this magnetic field, right? Earth's magnetic field. The source of Earth's magnetic field is lying beneath of our Earth, Earth surface, right? It's in the core. Our Earth's core, which is built up with molten iron or nickel, and because that is the source of this Earth's magnetic field. Electric currents from convection of molten iron nickel in the liquid outer core, right, which is in the around 3,000 to 5,000 kilometers deep, right, in the ground, in the inside of our Earth. This is happening, right? So because of the rotation of Earth, the Earth twists these currents, and it creates self-sustaining dynamo. The resultant is this kind of magnetic field, a dipolar field, like a bar magnet, but with some irregularities due to turbulent core flow, right? This is the reason we are having a magnetic field in our Earth system, right? But there are some structural changes also. Only north and south magnetic poles are dominant. The field lines emerge vertically there, aligned with the geographic poles, right? It is something different. But there we can see this magnetic field. And I told you there are some structural changes in the magnetosphere. You see, there is a Bohr shock, right? These are extra for your knowledge, right? So you don't need to think much about. But I like to teach you these things. They may help in different situations in the course, right? Even though this is not included in the book, right? This Bohr shock is the one major region in the magnetosphere, that is sunward side or day side. Bohr shock is the front line where the supersonic solar wind, right, abruptly slows and heats, right? And there is another one, turbulent region. Is a turbulent region of compressed heated plasma between the low Bohr shock and the magnetosphere, right? Then magnetopause is there, right? It is a boundary where Earth's magnetic pressure balances the solar wind pressure, right? And we call some cusps, polar cusps, right? The funnel-shaped gaps near the poles where solar wind particles can directly enter the ionosphere, fueling auroras, right? And then Van Allen belts. Those are the belts that trap and accelerate particles to near light speeds, right? So these are the things, and also interaction of the atmosphere with solar wind is also another thing, but extra for you. Actually, it is the thing that shape our constant battle between solar wind with our magnetic field. So this interaction determines space weather, auroras, radiation levels within our system, right? So I'm not going to talk about those things, but you can refer more, right? is the important thing and asked in lot of times in the question paper. Auroras. As I told you, auroras, which is a dazzling light show, is we can see such displays in the close to polar regions, right? They have two names depending on the hemisphere, right? When sun is emitting always beams, solar beams, and they are reaching our Earth's system. These streams of sun's energy particle, high energetic particles, we call as solar wind, meets the Earth's magnetic field. Then the particles are deflected due to our Earth magnetic field. But some get trapped and funneled toward the magnetic poles, right? Magnetic poles. And these particles, and so these such solar particles, mostly electrons and protons, collide with the atmospheric oxygen and nitrogen in the ionosphere there at about 80 to 100 kilometers. Do you think about such a level? Then they may excite, as I showed you earlier, making them light while they are going back to their ground level, right? So different colors can be seen. Oxygen may produce green, most common auroras, right? Or red auroras at high altitudes, while nitrogen can make blue or purple like violet like these things, right? It's explained here, and what I explained is in this figure, right? Not sure whether this worked. That is a kind of a, but okay, you can see not lots of images or videos in the web, right? All right, it's working, right? So these are the things I had to discuss today. But next day, 26th July, we'll have our second day school. We'll talk about the third one. I thought to do that also, that also today, but I had a lot to talk to. I had a lot to tell or teach about the two sessions.
Madam, can you tell bit about two and cats?
I told it at the beginning. Maybe you wasn't there at the beginning. I haven't decided it yet because it depends on the time sessions that I can finish before the NBT 1 examination date, right? I'll put extra workshops to cover.
I know, ma'am. Sorry, I was there. I am asking not about the capacity, but about the structure of the paper.
Same as NBT 1 examination papers, which has uploaded into LMS, right? All the NBT 1s and the answers has been uploaded. You can check all those.
Okay, ma'am.
There are lots of papers, right? And you can self-study. Everything is there. I have explained everything. So you can go through those papers and have a look to see the structure, right? Okay. I think that's all I have to talk to you. We will see this 26th July in the secondary school. So thank you for joining.
Thank you, madam.
You're welcome, Buddha.
Thank you, madam.
Welcome.